All right, so today get to have the last theory video, week 8. It's dealing with essentially DC motors and inclinometers. So DC motors in chapter 15, inclinometers 6.4. It's another sensor measuring the inclination of an object, and therefore its name. Basically what it consists of is the magnetized slug, so basically a piece of metal that's magnetic inside of a tube. And then as this thing tilts, gravity is going to want to pull the magnetized slug down the tube. That, of course, varies with the angle. So my gravitational force, weight times sine of theta. So proportional to sine of theta, essentially. And so the more the thing's tilted, the more the slug wants to flow down the tube. So to keep it where it is, you need to provide some sort of restoring force, and that's where the magnetized portion of this comes in. So if you apply a current, current's going to create a magnetic field. That magnetic field can then hold this magnetized slug in position. And so basically what you can do is measure how much current you need. The more current, the more this thing can hold. So as the angle gets bigger and bigger, the more current you're going to need to hold that slug in there. Now, of course, current is also related to voltage, and that's generally what we have for our sensors from week 6. So we can measure how much voltage we need to apply some solenoid to create a magnetic field to hold this magnetized slug in its current position based on the angle. And so after all that, all those different parameters in there, your voltage is proportional to just sine of theta. And so K is some constant involving things like the weights, the currents, magnetic fields, all those things that go into all those force equations. That's just one big constant, essentially, based on orientation, how big the slug is, all things of that nature. So K is some constant, can be calibrated in the lab, again, based on the scenario, and then your voltage is directly proportional to sine of theta, and so voltage can be related to angle theta quite easily that way. So generally what you have is this kind of black box scenario, a bunch of wires. You want to make sure you orient it properly. So in terms of measuring the angle, you want the wires to be at the top end to measure the proper angle. And these guys have generally 4 wires. So you have yellow, the voltage out, black and red, plus or minus 15 volts. So to power it, essentially, green for ground. And so that the out is, again, related to that angle. So they're very useful in aerospace applications, obviously, to find angles, angles of attack, things of that nature. The other thing today to talk about is motors, and there's a bunch of different types of motors that you can see. We're mainly going to talk about DC motors, servos, and stepper motors. Of course, there's a lot more. That's what these guys look like. So various types of motors have different pros and cons, obviously. DC motors generally work at very high RPMs and are relatively simple. But poor positional control, so to actually stop them at a certain location is not easy. And low-ish version of torque, again, that's kind of relative to the other options we have. And these are also for the majority of DC motors. There's some DC motors that are different from this. So this is just kind of general. Servos generally have high torque, very high positional accuracy, so you can kind of stop them wherever you want. Fast positional control. The problem with servos is only single rotation, so you can't have them be continuous rotation like a DC motor. The last ones are stepper motors. Again, very high precisional accuracy, high holding torque, but they're going to rotate fairly slowly, so low RPMs essentially, and they have more complicated control. So DC motors essentially a bunch of wires in a magnetic field. So to convert electrical energy to mechanical energy, you have electrical energy coming in, some sort of current. That current produces a magnetic field, interacts with the coil, and that makes it rotate. And so that rotation then goes out to produce some mechanical energy. So two components, a rotor and a stator. So rotor, something that rotates around. Stator, something that stays in place. Either can be a permanent magnet or a cold wire. So you can have either be the rotor or the stator. And generally high rotation rate, RPMs, 3,000 to 8,000 in general. If you want to go forwards or backwards, it's quite easy. Just reverse the polarity. So instead of having positive one side, negative on the other, just reverse that, and that'll make the motor go the opposite direction. We'll dig into DC motors a lot later in this lecture. This kind of is just a brief overview of it. DC motors are designed with some operating voltage, so there'll be some voltage rating, which is where it's most efficiently used. If this operating voltage is less than about 50% of that design value, the motor should stop rotating. If you try to apply voltage that's higher, roughly 50% higher, motor might overheat, and obviously that's a bad thing. So because of that, it's not easy to control the speed with the voltage. So more voltage, more energy, generally get more speed out of it, but you only have this very small margin of ranges where you can actually get to change that RPM value. So for example, if this DC motor is designed to work at 3 volts, and at that 3 volts, it rotates at 1,000 RPM or 10,000 RPM. If you want to work at 5,000 RPM, you can cut the voltage back to 1.5 volts, but again, at that point, you're roughly at 50%. And so if you want to rotate even slower than that, it's just going to stop, it won't rotate slower. So is there a better way to control the speed? Because that's something that you may want to do. And the answer to that is pulse width modulation. So you've kind of seen this in previous labs where you had this pulse width modulation. Not sure if that was for blinking the LED or doing whatever you had to do. But that's kind of the same scenario. So instead of having, so my signal can either be at the entire voltage. So again, if I have my 3 volts going in, I can do that for the entire, what's called a duty cycle. And so in that case, I just have a constant 3 volts. Or I can back that off into a 75% duty cycle. And so it's 3 volts for 3/4 of the time, and then 0 volts basically off for the other little bit of the time. 50% duty cycle, again, very popular, half the time 3 volts, half the time 0. And you can see here the average voltage over that little time period is 1.5 volts. And so that way, the motor is on and off, on half the time, off half the time. And if you have this time be very small, so in this case, time's in milliseconds, 500 hertz. So the motor basically on, off really, really fast. You don't notice that it's off, and so you still get what looks like fairly continuous rotation. In this case, at 50% duty cycle at only 1.5 volts, and you don't have to worry about the motor turning off because you're still actually giving it 3 volts, but only for half the time. Same thing for 25%, if you want to even less, just have less of a duty cycle. And so you can do things like recreate this sine wave. So in terms of, if you want the motor to kind of start at 0, go really fast and come back down to 0, then go the opposite direction. Pulse width modulate the signal. For these small parts, it's fairly small duty cycle. When you get to the faster parts, have an even higher duty cycle. And then as you come back down again, less and less of a duty cycle. Then we go negative, you're actually going down. Some opposite negative voltage. And so what you actually see in terms of the actual way the motor is rotating is you get this really fast rotation, then drops, then no power being put in, so it kind of drops off. Then you're really fast, or really motor's working really hard to increase that rotation again, and then battery goes, or voltage source goes to 0, so it drops off again. And so you have kind of have this somewhat sawtooth function as the motor turns on and off really fast to recreate this relatively sinusoidal speed graph, I guess. So servo motors are, again, much better for precise controls. If you want to actually stop at a certain angle, servo motor is really good for that. So servo is essentially a DC motor along with a gear train, a potentiometer, and a control circuit. So your control circuit basically controls what your DC motor is doing. And then you generally have a gearbox. So again, DC motors rotate really, really fast. Servo motors generally don't. So basically takes that super high, thousands of RPMs, and with all these gears, takes it down into roughly the 60 RPM range. What that does is it converts this low torque, high speed DC motor into a low speed, high torque device. And then your potentiometer here, it's actually measuring what angle the motor's at, essentially. So that helps you get the control and helps you get the really precise measurement. So that's how those work. Again, we have a position specified by pulse width modulated wave. So if you have a relatively short pulse width, so it's kind of the smallest version of it. It's going to be at 0. So that's what it's calibrated to for minimum pulse width. Anything smaller than that will stay at 0. Neutral is kind of in the middle. So kind of an average pulse width gets you up to 90. Max pulse gets you up to 180. Again, anything more than that won't really do much. Some of these go to 180. So in this case, I go from 0 to 180 over these pulse widths. Some of them go from 0 to 270. Just depends on the servo. The last types of motors are stepper motors. So stepper motors, essentially, you can tell it to move in certain increments. If you want to move by 50 degrees, 1.5 degrees, whatever it is. So this 4-coil stepper motor moves 50 degrees per step. So if you apply some voltage, telling it to move, you can have it move either 1 step or 2 steps, whatever you want to do. So energize that coil, that makes it move around 1 step, and if you energize the next coil, that'll keep happening. So those are your stepper motors. There's many configurations of these. Again, textbook has a lot more information on them. Generally, you have either 4, 5, or 6 wires. And it's, again, important to make sure you connect those to the right places. These guys, again, have very extreme positional accuracy. So in terms of their actual position, again, kind of comes down to this 1.5 degrees. So that's a fairly precise sort of measurement in terms of where this motor is. So from that, you can get very precise measurements of where you want things to be. So that's why they're used in 3D printers. 3D printers want to have it, everything be exactly where it is. So stepper motors are used a lot in those 3D printer applications. And so to measure the actual position of a DC motor or of any motor, or the velocity even, the way we do this is usually with an encoder. An encoder is essentially a disc with some holes in it, and then you have an LED on one side and a photosensor, kind of like a photodiode on the other side. And then as this disc moves around, so the disc is essentially attached to your DC motor or whatever type of motor you have. And as it rotates around, LED is going to shine some light through the holes. Photosensor is going to measure it when it comes to the holes, not when it's blocked. And then that basically goes to some circuitry, which tells you kind of where you are. So that guy can basically tell you either position and or velocity. So position in terms of where you are, velocities, kind of how many volts light's going through per unit of time. But with this guy, we can't tell direction, so we can't tell which way it's going. If you want to know direction, basically just have 2 rows of holes instead of just having the one outer row. You can also have one inner row as well, and then have 2 light sources, so 2 LEDs, also have 2 light receivers, so 2 photodiodes or something. And then as these guys see or don't see light, you can kind of tell if one's ahead of the other, you know it's going clockwise or counterclockwise. So again, for this guy here, position 1 and position 2, based on the relative orientations, 2 is slightly later than 1, and so that indicates counterclockwise based on where these holes are. If 2 is slightly earlier than 1, then it's going clockwise. So 2 rows gives you direction as well. So encoders can get even more precise if you do what's called quadrature. So quadrature for this particular encoder, I have 12 segments, so 6 slots, open and closed on each of the 2 rings. So basically what quadrature means is I'm now looking at not only when it's on or off, but actually the moment when it turns on or off. So in terms of single quadrature, so this guy's only looking at when does this thing turn on. So A turns on right there, turns on there, and turns on there. Double quadrature, now looking at when it turns on and when it turns off. So it turns on here, turns off there, on here, off there, on there, off there. If I do quadruple quadrature, now I'm looking at not only when does A turn on and off, but also when does B turn on and off. So looking at both signals, when do they turn on or off? And so I get a much more dense signal out of that, and so I can look at a much better resolution. So those are called incremental encoders, counting the steps of known angular spacing. More complex ones have all sorts of fun, complex patterns on them. So not just different holes, top and bottom, but all sorts of different holes and different lengths of holes and different locations. And so with this, you can find absolute position using kind of whatever this is, 10 or so rows of lights. And so you have much more resolution on this one, obviously, just based on which holes are shining through and which ones are not. So these are rotary encoders. Obviously, they rotate around with the motor itself. So you attach it to the motor and it rotates around with the motor. Have your LED, have your detecting device rotating around with it. And then that, again, will tell you where you are. So you have this encoder device attached to the shaft, and obviously it has some wires coming out of it, which again is going to tell you where you are. So A out and B out, again, kind of telling you when those are on and off. You need a ground, need some sort of voltage coming in, as well as the motor power. So this is the motor and encoder all attached to one thing. You can also have a linear encoder, so instead of having the rotary version we just saw, these linear encoders are used for precision measurement, mainly in things like CNC machines. Essentially, what you have here is a very fine grading, and that's going to give you a diffraction pattern. And based on that diffraction pattern, you can measure either position and or motion, kind of similarly to what we saw before. So instead of looking at position of holes, we're now looking at diffraction patterns. So those are the basics of motors in general. Now, as I mentioned previously, we'll talk more about actual DC motors. So basically, at its pure source, a DC motor basically just a wire rotating in a magnetic field. So I have some rotor that moves, that's usually my coil, and then has some permanent magnet outside of that. So north and south terminals of my magnet. Anytime you have a current moving through a magnetic field, that produces a force. So that's called the Lorentz force, IL across B. So L being the length along which current is passing, crossed with the magnetic field, gives you that force, and that's directionally in perpendicular direction, so right-hand rule. Don't know why there's a left hand here, but this actually does work it out. So S my force in the wire, again L's direction, the wire, which way the current's going essentially, and B is the magnetic field. So in terms of this direction down here, as a magnetic field going north to south, current in the wire, so L essentially going down, E going to the right, puts your right hand coming out of the page, so the force comes out of the page. In DC permanent magnet motors, so that's usually what we're going to be using. So permanent magnet motors, you have a fixed permanent magnet, so just like we had before, that north-south pole, and that's the fixed part, that's the stator part. And then you have a rotating element, the loops of wire, that's your rotor or the armature, another way to put that. So we have this rectangular loop of wires rotating around some axis, and the magnetic field is going to interact with the current in here and produce two forces, equal and opposite sides of this, equal opposite directions. You can find the torque, standard torque equation, R cross F. And so in terms of magnitude, that's 2RF sine theta. And so based on the current and the magnetic field here, the force always acts the way you have it here in the vertical direction. Its magnitude is going to depend on theta though, as we can see. An actual motor is very similar to what we just saw. I have some current coming in, so now I'm actually going to find my current come in this direction and go clockwise around my loop here. Magnetic field, I'm going to say is going to the left. So if I have magnetic field going to the left, current going along this line, that creates a force in the upwards direction on the left-hand side. Current goes down this side, which means the force goes in the vertical direction downwards on the right-hand side. In terms of the actual magnitude of the force, that's I times B times L. So current times magnetic field strength times length of my loops. And so again, my force is always either up on the left and down on the right, regardless of where this is rotating. So again, that's going to cause this thing to rotate. So it's going to make it want to rotate around. The problem is that the amount it wants to rotate, the torque, also varies with the angle. So the torque, 2R times the force, which in this case is IBL times sine theta. Once this thing gets to 90 degrees, the torque ends up being 0 because theta is not very well defined here. But this is essentially, this 90 degrees is the opposite of this sine theta. So the angle, this angle, sine theta, is the angle between the magnetic field and the current. So essentially when it's in this orientation, your force ends up canceling out because you have one force going up, one force going down, kind of equal and opposite, 0 distance between the two. So that's essentially your arc ends up being 0. And so no torque in that situation. And so what would happen if you actually did this, if you turned past 90 degrees and looked at the 180, so this basically flipped, current's going the opposite directions on each side, which means the force is going the opposite direction on each side. Essentially what you have here is an oscillator. You have something that's going to actually just rotate back and forth, and it's never going to actually rotate because it's going to, once it goes past 90, the torque then wants to make it come backwards, and then just end up kind of seesawing back and forth. And so that's not a very good motor. It's not going to actually rotate. We want our motor to continually rotate. So what can we do about this? The easiest thing to do is use a commutator. Basically what that is pair of contacts hooked up to the power source, and every time this coil turns 180 degrees, the current is switched. So once the thing turns 180 degrees, instead of having a scenario where the current's going in the opposite direction, and so the force in the opposite direction, we basically reverse the current and therefore reverse the force. And so once it gets past that 90 degrees, the current switches the opposite direction. And so instead of the torque pulling it back, it then keeps pulling it in the same rotation. And so it just keeps going around and around as opposed to stopping. So that's a good DC motor. It's not a great DC motor because there's still going to be a point where the torque is 0. So again, this thing's going to want to go up. And as it's going up, as the angle gets bigger and bigger, closer and closer to 90, the amount of torque gets smaller and smaller because essentially, again, that radius between your two loops is smaller and smaller and smaller, and eventually gets to 0. And so it's not great to have this variable torque as you move through that rotation. So how are we going to fix that? Easiest thing to do is use multiple loops, each separated by some angles. Instead of just having one loop like this, you have multiple loops at different orientations. And that way, when it rotates 90 degrees, even though this one has 0 torque, the other one got rotated, so it's now at maximum torque. And so obviously, the more loops you have, the less fluctuation of torque you're going to get. And that's obviously also a good idea. So there's kind of a better drawing of just 2 different loops. Again, that way when it rotates, it's going to keep on rotating around, no more dead spots, no more places where torque is 0. So that's the simplest one with only 2 loops. Generally you have more than 2 loops, you have many loops, more the better essentially. Each loop can also have multiple turns, so instead of just having one loop of wire at each orientation, you have multiple loops of wire. Again, that's going to give you more current essentially. And so more current means more force means more torque. So that's what the inside of a DC motor generally looks like. So in addition to the torque, another good thing to know about motors is the power that they can deliver, so how much power they can deliver from their shaft into whatever load we're putting it on. And so if you think about power, in terms of linear motion, power is force times distance over time, or force times velocity. For rotational motion, it's the rotational version of that essentially. So torque, rotational version of force, times angle, rotational version of distance, again divided by time. So that's torque. Angle over time is angular velocity, omega. Then these two are always parallel. So because they're always parallel, dot product in terms of magnitude just goes away. So torque times angular velocity gives you the power divided by a motor. So if you know the torque, multiply that by the angular velocity, and you get the power that is being generated. And because motors have wires moving in magnetic fields, anytime you have wires moving in magnetic fields, you get a back EMF from that interaction between the current and the magnetic field. That's going to oppose the applied voltage. That's why it's a back EMF. And then what that actually looks like is going to depend on what type of motor we're looking at. But anything you have the motor connected to, you have to realize that's going to be there. And so realize that whatever you have connected to it is not too sensitive to that back EMF. So kind of electrical construct of a motor is you have your motor giving off some back EMF, and then the coil of wires is going to produce some sort of inductance, and it's also going to produce some sort of resistance having to go through all those wires. So really what we want to know for the motor again is these things like torque and power. And torque and angular velocity, rotational speed, are obviously going to depend on the voltage and the current. They also depend on each other. So if we look at circuit on the previous line, apply Kirchhoff's voltage rule to it. Some of the relationships between the magnetic field and currents. For a given voltage source, found that the torque is some constant T0 times 1 minus omega over omega 0. And these values, T0 T0 is called the stall torque. That's what you get at 0 rotational rate. Omega 0 is the freewheeling speed. That's what you get at 0 torque, essentially. And then between those two, you have a straight line. So for some given voltage, you have a straight line given by that equation. If you increase your voltage, you essentially increase both T0 and omega 0. And so you again get a straight line, just a slightly different location, same slope as well, essentially just different y-intercept. So in terms of that torque produced by a motor, friction is going to slow that down, obviously. Mechanical system being driven is also going to be a factor in that. If you don't have a load, friction is a fairly weak function of omega, so your torque is essentially constant. As your voltage is increased, omega increases, so your current is essentially constant. Again, those are things that hopefully you're going to see in lab. And so this curve is called the motor curve, basically giving the relationship between torque and angular speed. If you have a load that's present, the torque demanded by that load is going to increase with rotational speed. And so anytime, whatever you connected your motor to, the amount of torque that's necessary generally is an increasing function of omega. And so that's called the load curve. Again, it's going to depend on what thing's actually connected to. That's how we get that curve. And then once we have our motor, we have a motor curve, so we know what it looks like in terms of I attach some voltage to it, and so I get some curve that the motor responds to in terms of torque and rotational speed. I have some load curve, so this is the curve that I need to match for my application, whatever it is. And basically where those two curves intersect, my load curve and my motor curve, that's the operating point. So operating point being both the rotational speed as well as the torque produced by the motor. If I want to change those things, I can have a higher voltage. Applying a higher voltage is going to increase both the torque and the rotational speed. And again, wherever that intersects the load curve, that'll be my new rotational speed and my new torque produced by the motor. The last two things for the motor are the power as it's related to the efficiency. So in terms of efficiency of the motor, efficiency of anything is power out divided by power in. So power in is the electrical power supplied to the motor. Power is current times voltage. Power out, we just derived this equation, was omega times T, rotational speed times torque. And so dividing those two gives me the efficiency. If I relate those into currents and voltages, that's 1 minus IRA over BS. Essentially, this just takes into account the loss due to armature resistance. So this IR over BS is how much power is lost in the resistance due to all the wires. And essentially, that's the only thing that's stopping this from being 100% efficient. So obviously, this is an approximation because there are other sources of inefficiencies, such as friction in the bearings, air resistance, eddy current losses, and hysteresis. If you look at what we've seen so far in terms of rotational rate and torque, power, and efficiency, so my torque curve, the motor curve is a nice straight line. The power is parabolic, essentially. So torque is linear. Power is torque times omega, so that makes it quadratic. And then efficiency is this other curve. So relatively linear at the beginning, then reaches a peak somewhere in the 85–90% range in terms of RPMs, and then drops off relatively fast as well. And last thing to talk about are generators. So if you want a generator, something to store or Yeah, something to store electrical energy. You can basically take a DC motor and run it in reverse. So a DC motor in its forward setting, you put in electricity, you get out mechanical energy. If you do the opposite, if you put in mechanical energy, you turn that shaft. That's going to turn your coil in the magnetic field, and that's going to generate some current. So it's basically going to generate electricity. So instead of converting electricity to mechanical energy, a generator converts mechanical energy into electrical energy. And that's how a lot of things are done. So if you want to charge a battery, like I said, you have this back EMF caused from this mechanical rotation, and that is going to create some current into your battery to charge it. If your battery has some voltage into it, then you have to make sure that you're cranking the mechanical energy at that creates a higher back EMF to that voltage that your battery is producing. Otherwise, you're not going to charge the battery. If you don't even have a battery there, so if the battery is zero, you have basically what's called electromagnetic braking. So that's essentially how brakes on electric and hybrid cars work. Instead of having real brake pads, you just basically in a situation where you're taking the actual engine from the car and you're running it in reverse. And so it's essentially taking your momentum from the wheels spinning, that's your mechanical energy coming in, and that basically runs your electric motor in reverse. That motor running in reverse charges the batteries in the car. And so again, that's how hybrids and electric cars work. That's how they get recharged. And so I find that pretty interesting. Hopefully you do too. As usual, do some examples in class, and your labs will be very related to this subject.